Algebra 2, Unit 7, Section 5, Exponential Change. A lot of this is going to be stuff that you talked a little bit about in Algebra 1, which goes for a lot of things in this course. We give you a taste of it in Algebra 1 and then expanded it in Algebra 2. And that's the exponential growth and decay formulas. Like, this should look familiar to you. You spent a little bit of time with that. And this is the exponent chapter, so we're kind of bringing up a lot of that stuff again so that we can go deeper with it. So this is kind of a review video of things hopefully you already know, but if in case you don't, you'll learn it right now. So here's your basic exponential change formula. And then what you're more familiar with is this, and let me write this down here so I can illustrate on it a little bit more. A equals P times 1 plus R to the T. And what this stuff stands for, our P here stands for principal, or initial value. And 1 is the number 1. R stands for rate, and T stands for time. And so a question like this, Cassandra bought an antique dresser for $500. If the value of her dresser increases 6% annually, I'll talk more about that, what will be the value of the dresser at the end of 3 years? So A is kind of the answer, but it's the value after a T amount of time, basically. So like, this is really kind of like your Y and your X, if we're going to do this graphically or something like that, where your initial value doesn't change and your rate doesn't change. This concept of annually here, that has to do with compound, which we're going to talk about in the next example, so I'll come back to that. But for now, this is our basic formula. So what we would plug in here is that our value of the dresser after T years is represented by 500 is what she bought it for. So that's the initial value, or the principal value. And then 1 plus R. Now R, it's important that it is your percentage divided by 100, because what we really want is the decimal form of that. So 6%, if we did 6 divided by 100, is 0.06. And it's important to do that. Otherwise, if you did 1 plus 6, it's going to be a much quicker growth than what we're looking for here. And your answer should make sense. If she bought something for $500, it increases 6%. 3 years later, I'm expecting something that's still going to be in the 500s. If you're getting something that's worth billions of dollars, then we should all be investing in antiques. But 1 plus is 0.06 is 6%, and we're raising it to T. T is time in years, so the end of 3 years, that would be 3. And we're going to use our calculator to solve this stuff. So let me get that up and running. Now, one thing that this is, one of the things that I highlighted or underlined was increases 6% annually. What if it was decreasing in value at an exponential rate? It was decreasing annually. A lot of times we talk about population, which is sad, but we use population as an example of an endangered species that is decreasing at a rate of 6% annually. How many will there be after 15 years, something like that? Well, this formula would change only by this plus sign. It would be a minus sign if it is an exponential decay as opposed to an exponential growth. So increasing is growth. We'll have a plus sign. We're increasing by 6%. And a decay would be it's decreasing. And so when you add this together, the parentheses, we had 500 times 1.06 to the 3. Now this 1.06 as a percentage would be 106%. And that makes sense, because if it's increasing 6%, that means it's going to be 106% what it previously was, right? 100% is just going to stay the same. Like, if it was $500 and it's 100% of that is $500. So if it wasn't changing at all, then that would be it's not wouldn't be changing at all. 100% of 500 is 100%. But if it's increasing by 6%, then it's going to be 106% of what it was. So that's kind of why that is like that. But anyways, we could use our calculator to do this math for us and type in 500 parentheses 1.06, close the parentheses, raise it to the third. And that will give us a value of 595.508, but 595.5 will round to 596. All right, the next example, number 16, gets into the concept of compounding. So what if it's not an annual thing? Meaning annually, meaning that we take 6% of whatever value we have, and that's going to change every year. Like 6% of 500 is, a specific number. But then when I increase it to whatever it is, I then take 6% of that new number. And that's why it's changing exponentially. If it was increasing the same amount each year, that would be linear. But this is what we're saying is whatever our percentage is, it gets applied more than once a year. And that's what compounded interest is. And so the formula changes slightly. We still have the A equals P parentheses 1 plus, but your rate R is divided by N, and your T time is multiplied by N. So we add those two pieces. And what N is the number of times the interest rate is compounded annually. So in this question here, $5,000 is invested. So that's going to be your initial investment, the principal. 1 plus. Into a rate at 3.5%. And now divide that by 100 to get the decimal version. I know that's a decimal, but I mean, dividing by 100, we get 0.035. And so it's compounded quarterly. So quarterly, that's where N comes in. And so there's a couple different versions of this. Annually would be 1, and so the formula would be divided by 1 times 1, and that'd be exactly what we had here. Semi or biannually would be twice a year, so we put in a 2 there. Quarterly is 4 times a year. There's 4 quarters in a dollar. There's 4 quarters in a game. There's 4 quarters in a year. So compounding quarterly, we're going to divide our rate by 4, but we're also going to multiply our time by 4. We want to know 18 years. So T is 18, but we'll have to do 4 times 18. And because we want to raise it by how many times we apply this, increase, this percentage, this growth. And so if we're doing it 4 times a year for 18 years, if we multiply 4 times 18, that's going to be how many times the interest was applied or calculated. And so, we could, again, just type this into our calculator. And as this course goes on, this is really where we first start having to see some really complicated calculator stuff. You have to get very good at typing things in here the right way. And it's a lot of parentheses, and that's where you have to be careful. You can always do pieces at a time and second answer, but we're going to have some pretty complicated stuff that we need to type in here, way more complex than this. So make sure you're very careful with parentheses. So 5,000 parentheses, and then 1 plus, and then here I have a fraction here, and I should really have that in its own parentheses as well. But I actually don't think I'm going to need that here in this particular case because when we do, PEMDAS, we multiply and divide before we add and subtract anyway. So the calculator is going to know to divide that before adding it to 1. But I could have it in my own parentheses. And raised to the, now here I could, separately figure out what 4 times 18 is and type that in here. Or if I want to do 4 times 18, I can do that. Now I have a newer calculator software on here where it actually raises up. If you don't have one of those calculators where it just, when you hit the exponent key, it actually puts that on your screen, then you do want to have open parentheses, 4 times 18 close parentheses. And basically, if you just don't get the same answer as me, then, try typing it in a little bit more accurate with a little bit more parentheses. And so we get $9,362. And that sounds reasonable. It's gone up a lot, but we're talking about 18 years compounded quarterly. That's a pretty lengthy amount of time. So A comes out to be, let me just put that back on the screen, 9,362.36. All right, so what if I were to compound it, that's quarterly. What about monthly? Well, monthly, compounded monthly, we would have N equals 12. Do we think that would give us more or less here? Well, the more times you apply the interest, the more increasing it's going to have. So the more times something's compounded, typically, the larger value. So let's look at that. What if we did 5,000 parentheses 1 plus 0.035, but this time divide by 12 and raise it to the 12 times 18 and see what the difference is. And we see that it did go up, 93,079 instead of 93,062. So it's not going up drastically, but it is going up. I mean, what if we just did annually? What if it was, just compounded once a year like we had in that first example? Then it'd be 1 plus, not negative, 0.035 raised to the 18. So you just divide by 1 times 1. We don't really need to type that in. We see it's 92.87. So compounding does increase it. Compounding quarterly went up to 93.62, and then monthly 93.73. So it is going up and up and up. What if we keep going? So instead of monthly, you did, daily. What about, every hour, things like that? What's going to happen? Well, this gives you an example of that. You don't have this on your paper, so just take a look at it. You don't need to write any of this down. But what this is showing is, let's simplify things. What if our principal was just 1 and our rate is 100%, so 1, and we just want to see what is the difference of compounding yearly, that's once a year, semi-annually, twice a year, quarterly, 4 times a year, monthly, 12 times a year, and so on, weekly, daily, hourly, every minute, every second. The more and more we compound, the larger this is going to get, but you'll see that the growth does kind of slow down. That from once a year to twice a year goes up 0.25. And then twice a year to 4 times a year it goes up to 0.44, which is only, it's less than 0.25. And then monthly it's 0.6, so it's about 0.2. Then 6.1 to 6.9, so it's only went up like 0.08. Then it goes up to 2.714, 2.718, 2.7182, 2.71828. And so what you see that it is slow, it is still increasing, but it is slowing down. It is approaching a limit. And the limit it is approaching is actually a special number you have in your calculator. Second division sign, we get a little e. That is 2.7128, so on, so on, so on. That is a special number. The number e, we call it the natural number. And it was discovered by a guy named Euler, whose name does start with E, although he swears that he named it the letter E because it stands for exponential, not his name. But most people tend to think it's because Euler discovered it, and it's Euler spelled with an E. But what this is a naturally occurring number, very similar to pi. You're very familiar with the irrational number pi. Well, E is the next most common irrational number we see in mathematics. In fact, we tend to use E more and more often, going into, continuing with this course, and then when you take pre-calculus and calculus and stuff like that, you tend to see E just as much as you see pi. These are the two most common and useful irrational numbers that we have. So E is about 2.7, where pi is about 3.14. But that's what happens is the more we compound, the closer we get to that naturally occurring number. And we see it all the time in nature and stuff like that, but we use it often in exponential stuff, especially in finance. So sometimes we will talk about, instead of compounding quarterly, monthly, we'll say compounding continuously. And in that case, we have a special formula we use other than the compound formula. And that's our answer is our principal times E raised to the RT, where R is still rate and T is still time. So this is a special formula for compounding continuously, meaning it's constantly being compounded. And that's going to give you the highest, amount of applications if it's constantly happening. So this is a letter E. It's not a variable. It is a specific number like pi. So Emma's parents deposit $5,000 into an account, and her freshman year, so this is times E. The account is 5%, so that is 0.05, and we want to know what's it going to be worth in 4 years later, so times 4. And so to type this in, we'll do 5,000 parentheses, and we actually have to type E, close the parentheses, raised to the 0.05 times 4, and that will give us the value there. And so we're going to talk a lot more about this number E, especially when we get into logarithms. It's a very useful, interesting number. Like I said, you're very familiar with pi at this point, so E is kind of a new one for you. It's the first time you really see it in high school, but you're going to see it a lot going forward. All right, that's it. Sorry for the long video. A lot to cover here, but we're going to be working with these exponential functions quite a bit for the rest of the year. See ya.